Hello again. This video is on chapter 11. I hope you're doing well, and let us get started on that. All right. So chapter is about a new distribution that you probably haven't seen before. Now, you have seen distributions like normal distribution, right? And you have seen T distribution, which kind of looks similar. You have seen uniform distribution, right? You have seen exponential distribution. These are all different chapters we have talked. And in all of these, in these three for sure, x could be here anywhere from negative infinity to infinity, right? X can be value here as well. Here x is between two numbers, a and b, right? For exponential, x is greater than or equal to 0. And now we want to talk about a new distribution. It's called chi-square distribution. And that is used for many application problems. We're going to talk about some of them in this chapter. All right, so that's a new distribution. It looks like, so basically 0 before x equal to 0, this has graph is just 0. After 0, it has a graph that is skewed to the right. Kind of looks like that. That is the chi-square distribution. And we're going to talk about that in this chapter and use it in many application problems. All right, so what are we going to do in this chapter? We're going to do something called goodness of fit test. Goodness of fit test, and we're going to do something called independence test, and we want to talk about homogeneity test, and then lastly we want to do talk about testing a claim about the distribution, about the population variance or standard deviation. That's what we're going to do in this chapter. So let's get started. This chi-square distribution first was introduced by Pearson in 1900. He published a paper on chi-square test, and it's considered to be one of the foundations of modern statistics. So in this paper is that Pearson investigates the test of goodness of fit. So we're going to talk about that in this chapter. All right, so what is this distribution about? Well, if you take the standard normal distribution, z, right, and you randomly sample k numbers from the normal distribution and square them and then add them, and if you keep doing that, keep taking samples of k numbers and then square them and add them, right? If you keep doing that, then those numbers that you get, the sums, they're all called chi-square numbers, and they make a distribution like that. That's the distribution basically. So these are normal numbers, and you add them together, you square them and add them together. So obviously this number is always positive, right? So that explains the distribution of chi-square that always starts from 0 and is skewed to the left, to the right. Okay. Now the mu of this distribution, the average of it, is the same as degrees of freedom, and degrees of freedom is similar to what we talked about T distribution, right? T distribution had degrees of freedom. So degrees of freedom is the same as mu. Degrees of freedom is the same as mu. And it's a little bit to the right of the peak here. You see the peak here? So the mu is about right here usually, right? Is it right of the peak? And the standard deviation of this distribution is just the square root of 2 times. Remember, mu is the same as degrees of freedom. So to get a feel of what this distribution looks like, I'm going to just go to this that I created with a GeoGebra. And I'm going to show you this distribution with different degrees of freedom. So that's the degrees of freedom of 2. So let me move it this way. So that is, forget about that blue graph for now. The blue graph is the normal distribution that kind of matches the chi-square distribution. So just concentrate on the red one. The red one is the chi-square distribution with different degrees of freedom. As you see, it changes as I change the degrees of freedom. And notice that, you see, the mu is 39, and the peak here happens about right here. So the mu is just to the right of the peak, right? That's about 39. And the standard deviation is, of course, the square root of 2 times 39, which is 8.883. Now, something, if you notice here, now you can look at the blue graph, which is a normal distribution. And when I go to the degrees of freedom is about 100, right there. You see the red graph kind of matches the blue one. And the blue one here is a normal distribution with this mu and this standard deviation. So if you graph a normal distribution with this mean and this standard deviation, kind of looks like the chi-square distribution. Okay? All right, so that is what it looks like. So I'm going to go back to what we were doing here and continue. All right, and I just explained this fact that if the degrees of freedom is 100 or more, then the normal distribution with this mean and this standard deviation approximately looks kind of like the chi-square distribution. All right, so the test statistic here, when we do the testing, the test stat is always greater than 0. So it's going to be over here, right? Test stat is going to be somewhere over here. All right. So chi-square distribution is a useful tool for assessment in a series of problem categories. These problem categories are listed here, some of them. Whether a data set fits a particular distribution. For example, let's say somebody claims that, so let's say this is expected. So these are a bunch of numbers that we expect to get based on someone's claim, right? And then observe. These are numbers that we got from observations. Now, how do we go about testing whether this claim was right or wrong? Well, we're going to take the differences, right? So we're going to take the differences, observed minus expected, and square them, and then divide by expected, them all up. This number will be our chi-square number. And then we're going to use it as test stat in chi-square distribution, just like we did with normal and t-distribution. And then we do the same thing. If this chi-square falls over here, right, then we find that area, and that would be our p-value. That's the idea. And the same is true here, whether distributions of two populations are the same. So somebody says that we got two populations, number 1, number 2, right? And then we have a bunch of numbers from this population. We have a bunch of numbers from this population. Now the question is, are these the same distributions? Well, again, we take the differences and we build this chi-square, and then we see what the p-value is. Whether two events might be independent or not, again, this is when we have a table and we've got two variables, one here and one over here. So one variable is here and one variable is here with different values. We want to know if these two variables are independent. So for example, cigarette smoke and getting cancer, right? Are those independent? Well, if they can prove that they're independent, then the smoking doesn't cause cancer. Well, it turns out that they do depend on each other. So that's another test we do. Again, we are going to find a chi-square from this, and then again put it find the p-value and do the test. And then also we use it to talk about whether someone's claim about variance or standard deviation is to be rejected or not. We're going to do that. So this chapter we're going to do all of these. So let's start by goodness of fit test. That's what it's called. So in this type of hypothesis test, you determine whether the data fit a particular distribution or not, right? So somebody claims that the data fit certain distribution, and we're going to see if that is actually we can reject it or not. All right. So the null and alternative hypothesis can be written in sentences or maybe stated as equations or inequalities. So what we're going to do, again, in this kind of test, we have expected values and we have observed values, right? And what we do, we're going to take the observed values and subtract the expected value, square it, divide by expected value for every one of these, and then add them, right? And then add them. And that would be our chi-square. And K here is the number of different data cells or categories that we have here, right? And the degrees of freedom would be that number minus 1 for the chi-square. So degrees of freedom would be whatever that number is minus 1. Okay, so now let's do that. So the goodness of fit test is almost always right-tailed. If the observed values and the corresponding expected values are not close to each other, then the test stat can get very large, right? So how does this work? Well, basically, if we have observed and expected, if they are really close to each other and you take the differences, well, the differences would be small, and when you square it, you get even smaller numbers, and when you add them and you divide and you add them, you get a really small number. So when you go to chi-square distribution that starts from 0 to infinity, so the number that you get, the chi-square that you get out of this formula is going to be a small number right here somewhere, right? Depending on how big this number is, calculate the p-value after it, the area to the right of it. This is the area that we're going to compare with the alpha of the test. Remember chapter 9 and chapter 12? So if alpha is 5% and this number p-value ends up being, let's say, 0.01, then this is smaller than 5%, then we reject the hypothesis that says what? That says that this data actually fits what is claimed, right? That's the idea. So let's do a specific example here. So in this example, these are the number of absences that a faculty at some college claim to be true, right? So that means out of 100 students, the faculty thinks that 50 of them would have absences from 0 to 2, 30 of them will have 3 to 5 absences, 12 of them from 6 to 8, and so forth. And then actual number of students is people actually took a sample from students, and they found out in that sample 35 had 0 to 2 absences, 40 from 3 to 5, and so forth. Now, one thing about this test is that these cell numbers, these numbers expected, right? These numbers have to be greater than or equal to 5. In this case, they're not great, at least 5, greater than or equal to 5, right? These are not, these two, this one. So what we're going to do before we start doing this test, make sure we satisfy this test, this condition. We're going to combine these last two together and make a category called 9 plus. So 2 plus 8, we put 8 here and make this 9 plus. And 4 plus 1, we make this 5 and make this 9 plus, in order to be able to do the test. Okay? So, so that's the first thing we want to do. So let's do that. So here you go. Now we add these two. So now we got 8. And we add these two, we got 5. Okay, now, so can you use information as it appears in the charts to conduct goodness of fit test? No, because of that problem, but we fixed it. Can we do a goodness of fit test now? So the null hypothesis is that the expected number of absences are actually these, and the alternative says they're not. Right? So let's see. So determine the null and alternative hypothesis. Well, here's the null hypothesis and here's the alternative hypothesis, right? Now, let's do the test. We don't have alpha here, but doesn't matter. We can find p-value, right? So let's do the test. So how do we do the test? Well, we're going to take these numbers, right? Put them in L1, right? So let me bring the calculator. There you go. Oh, we've got 2 calculators. Only need 1. All right, so what I'm going to do is go to Stat. You know how to do that already. Go to Edit. And I already put the numbers in here. You see, 50, 30, 12, and 8. And I'll put the numbers here. These are actual numbers, right? These are actual observed values, and these are what? Expected values. So I put the expected values in L, and I put the observed values in L2. Now in L3, let me erase it and do it again. So what I'm going to do, I'm going to put that formula in. So what's the formula? So let me, first of all, the K is 4. We've got 4 categories. 4 minus 1 is 3. So standard, the degrees of freedom is 3. And then now is, I'm going to use this formula here, right, in L3. So the formula says observed minus expected squared divided by expected. So I move the cursor on the title on L3, and I put parentheses. Now observe, remember which one was observed? Was L2. I'm going to put L2 minus L1, and then squared, then divided by what? By expected, which is L1. And then when I press enter, calculator is going to calculate those numbers for me, right? There. Now I'm going to go to home screen. What I have to do, I have to add these numbers, right? I have to add all of these. All of these now, they're in L3. So I go to second and list here. Go to math. and then pick sum, number 5, and put L3 in it. And I get 14.29. That means my test stat is 14.29, right? Okay, so that's my test stat here, 14.29. Now, I know the distribution is a chi-square distribution with degrees of freedom of 3, which looks like this. And I did this with GeoGebra, but you don't have to have the graph. You can use a calculator. So calculator can find the area after what? 14.29, 16, and so forth, right? So that's the number right here. So we want to find the area to the. So it's a small area, but the calculator can find it. And notice that it's a very small value. It's less than 0.5%. So that means even if alpha is 1%, we still what? Reject. So our decision here is that we're going to reject the null hypothesis that what? The student absenteeism fits faculty perception. So faculty perception was this, and we are going to reject that. Well, basically, we have enough evidence to say that's not true, right? That's the idea of testing, okay? So let's do some more. Here's another example. In this case, employers want to know which days of the week employees are absent in a 5-day work week, Monday through Friday. Now the question here is that, is it true that people really are absent randomly? Doesn't matter what day. That means if you collect data, then the number of absences in each day would be just randomly spread out. There is no concentration of absences in any one day. That's the idea. So it says, suppose a random sample of 60 managers were asked on which day of the week they had the highest number of employee absences. And these are the results. So these are observed values. For the population of employees, do the days for highest number of absences occur with equal frequency during a 5-day work week? Test at 5% significance level. That means if the null hypothesis says that the absences occur with equal frequencies during a 5-day week on any day, do we have enough evidence with this data to actually test that? Yes, we do. We don't know, but we have enough information to do the test. So let's do the test. So what do? We write the hypothesis. Of course, the null says, yes, these are, it will occur with equal frequencies. And the alternative says no, right? They are not. Okay, so what we do is we're going to assume these are observed values. And what should the expected values be? But remember, the total is 60, right? If we assume that the days happen randomly, spread out, then 60 absences should be randomly, equally spread out in 5 days. What's 60 divided by 5? 12. So that means we expect, based on the null hypothesis, we expect that to get what? 12 absences in each day on average, right? But we didn't. This is 15. This is good. This is not good. This is not good. This is not good. So now the question is, are the differences here, are these differences significant to reject the null hypothesis? And the answer is, well, we don't know yet, but we can find out. All we have to do is, again, put these in L1 and put these in L2 and do what we just did. So let's put the expected in L1 and put expected in L2 and the observed in L1, right? You just put those numbers. You can pause the video and put these in your calculator. And then in L3, we're going to go to L3 title and put a formula in there. The formula should be L1 minus L2 observed minus expected squared divided by expected. And then press enter, you get these numbers. Then you go to home screen and add them. Sum L3, you get 3. So what we have is basically these numbers. If you want to do it by hand, you could without a calculator. You get 3. So 3 is our test stat, right? So what's the degrees of freedom? Well, how many do we have? We have 5 of them, so degrees of freedom is 4. So we are going to use the calculator and find the area to what? To the right of a chi-square distribution with degrees of freedom of 4 to the right of 3. That's that area. So we can go to second distribution and find chi-square CDF, just like chi-square, just like normal CDF or TCDF, we have chi-square CDF. And then what goes here is lower, upper degrees of freedom, right? Lower, upper degrees of freedom. You put comma. And the answer is 55%. So that means this is right way over here, probably it's 3. Right, it's not here, maybe it's here, but that's 55%. So what does that mean? That means the differences are significant, right? That means we cannot reject the null hypothesis that says these are actually all the same. So we kind of have to support that because we don't have evidence against it, right? And this might be surprising because some people think that people will be absent more often on Monday and Friday. But that doesn't seem to be true based on the data we have here, right? Because they think they have like a 3-day weekend, but that's not true according to the data we have here. Maybe people, companies don't have sick days, many companies, and people don't want to be absent and lose money. Maybe if we had sick days, that would be maybe true. We're not sure. We don't have data to support it. But according to what we have here, we are going to fail to reject the null hypothesis in this case, right? So conclusion, at 5% level of significance from the sample data, there is not sufficient evidence to conclude that the absent days do not occur with equal frequency. All right, so that's the idea of fitness of and goodness of fit test. I keep saying fitness. Goodness of fit test. All right, we can also do this with a test if you have this test on your calculator. So let's see, you can check and see if you have this test. Now remember, we have to put what? We have to put the data in L1 and L2 first before we do this test, and I have them here. And notice that L1 is actually my expected and L2 is my what? Is my observed. But here observed is in L1, so I can switch them when I do the tests. So what I have to do is, remember I have to switch these two. So I'm going to go to stat, and you go at the end and see if you have a test called chi-square goodness of fit test. You see it here, chi-square goodness of fit test. And looks like I do, is right there, right? So I'm going to pick that one. It says, where did you put the observed? Well, I put the observed in L2 actually, and I put the expected in L1. You got to make sure that you do this correctly, right? And degrees of freedom, of course, is 4, and you can calculate or draw. If you calculate, you basically get the same. Well, I don't have these numbers. I have the previous problem numbers, right? I forgot. well, let me put these numbers in here now that we are here. I'm going to do exactly the same thing. So 15 and 12 and 9 and 9 and 15, and in L2 I'm going to put, well, it's just all 12, right? 12, 12, 12, 12, and 12. Okay, now I'm going to run the test. So stat tests, I'm going to go to goodness of fit test, and my observed now is in L1. I need to fix that, and my expected is in L2, and degrees of freedom is 4. So calculate, you see I get that p-value, and what you see here, it says contributors. Contributors are basically those numbers, differences, right? So if you take the differences and square them and divide, those numbers become these numbers right here. Those are the contributors. We don't need them. We just need the test stat, which is right there, and the p-value. And if you graph, you're going to, so if you graph, you're going to get this. That's calculate, that's graph. So we can do this with the calculator if you have that test. If you don't have that test on your calculator, just do what I just did previously, right? All right. Now here's another one. Again, we want to compare. I'm going to let you read this in the notes and do it yourself. We're going to compare this column with this column. The only difference is that here, these are given in percentages. So you have to take the total, which is 1,000, right? 1,000 student. And you have to find the percentages of 1,000 and put it here. And then put these as observed in L1. Put these in L2, not the percentages, but the numbers. You get the numbers by taking 10.2% of 1,000, 8.2% of 1,000, and so forth. So you can compare them. I'll let you read this in the notes. Or we can do it. Actually, it's not that hard. I mean, it doesn't take that long. Okay, so what we're going to do is this: perform a goodness of fit test to determine whether the local results, which are these observed values, follow the distribution of the U.S. AP examinee population based on ethnicity. So we're going to compare this column with this column. So we don't care about this column for now because we're not asked about it. We're asked about this one and this one. So let's do that. So what we're going to do is we're going to put the observed values in L1, right? You can pause the video and do it. And then in L2, we're going to put these percentages, right, of 1,000. It's really easy to calculate because if you want to find 10.2% of 1,000, well, you know we can't work with percent. We have to convert it to decimal. If you convert to decimal, you move the decimal to the left 2 places. You get 102.102. If you multiply that by 1,000, well, you move the decimal to the right 3, right? So to get each number, move the decimal to the left 2 and to the right 3. You end up with 82, 102, 155, 6, and so forth. If not, just use a calculator. So you get the percentages of 1,000, you put it as expected, right here, and then use that test, goodness of fit test. Or you just go to L3, put that formula in there, and find the sum. That's your test stat. So if you have this goodness of fit test, then the answer is right here. This is your test stat, and this is your p-value. And notice the p-value is about maybe 2%. And if you're doing at, depends on what alpha is here, but the p-value is about 2%. Okay? So it says perform a goodness of fit test to determine whether the local results follow at 5% and at 1%. Okay, well, If we do it at 5%, this is smaller than 5%, so we reject. If we do it at 1%, then we fail to reject because this is more than 1%, right? That's p-value. So at 5% we reject, at 1% we fail to reject, right? And of course, these are the terms that the sum of which is actually 13.4. These are the numbers that you get if you actually do it by hand, right? Observed minus expected squared over expected. At every value, those are the numbers that add up to this number. But we don't have to really know that. We just want a sum, and the sum is given here. All right, so we did that one too. And we leave these. I leave these for you to do by yourself. Is it good? No? Okay, we do it. All right, suppose you flip 2 coins 100 times. The results are 20HH, 27HT, 30TH, and 23TT. Are the coins fair? Test at 5%. Now, if the coins are fair coins, you know every one of those has the same probability of occurring, right? So that means what? That means we were supposed to get 25 of this out of 100, right? They did it 100 times. We are supposed to get 25 of these, 25 of these, 25 of these, and 25 of these. That means with one head, we would have 50 different, times we would get one head, and 25 times we would get 2 heads, and 25 times we would get no heads. So that's our expected values if the coins are fair. But what happened? Well, this is what happened. Now, of course, they're not the same, but the question is, are the differences statistically meaningful for us to reject the idea that the coins are fair coins? And the answer is, well, let's see. We put these again observed in L1, we put expected in L2, we run the test. What's the p-value? 34%. What does that mean? That means that under the chi-square distribution, we get these numbers, the differences, right, and add them. If we keep doing that, according to the data that we have, the differences when we square them and divide and add, there are going to be a number such that the area to the right of it is about 34%. That means just by chance, even if the coins, given that the coins were fair or are fair, we still would get numbers that different from what they were supposed to be just by chance. So this doesn't prove that there is something wrong, right? That's something that by chance can have, we can get numbers even that big or greater than that 34% of times. Now, if our p-value, if our test stat ended up being something like maybe something over here, and the probability of getting that number or bigger would be like maybe 0.0001, then we would reject, of course. We would say no. If the coins were fair, then we wouldn't. The only way we could gotten this number is with this probability, which is really small. All right, so in this case, we don't have enough evidence to reject the null hypothesis that the coins are fair. So basically we say the coins are fair, right? And that's the idea. So there's not enough evidence to conclude that the coins are not fair, right? All right, so at any level, really, 5%, 10%, 1%, doesn't matter. We still wouldn't have enough evidence to reject the null hypothesis. All right, So now we want to do something else that's called test of independence. What is that? Well, that is when we have two variables, usually given in a contingency table like this, just like chapter 3, remember we did probabilities. So here we have two variables. One of them is here and has these values, and one of them is here, and these are the different levels of that variable. The values are here. These are different levels. So this variable is a type of volunteer, and we have volunteer coming from community colleges, four-year colleges, and non-students. And this variable is number of hours that people volunteered for, and that has three levels: 1 to 3 hours, 4 to 6 hours, 7 to 9 hours. Okay, so that's the variable that has three levels, and this has three levels. Now the question is, are these independent? That means the number of hours that somebody volunteered, is it independent of where they come from, or somehow they're dependent? Now, to do this, we have observed values and we have expected values. The only thing is that the observed values in these problems are given always. You have the observed values. So in this case, they took 830 people and asked them what, and they looked at the data, see where they come from, and how many hours they volunteered for. For example, 96 people volunteered for 46 hours, and they came from community colleges, and so forth. Now, the question is this variable independent of this variable? And the answer is from chapter 3. Remember we said, if two events are independent, probability of A and B would be probability of A. Normally, probability of A and B is probability times probability B given A. Remember, events are independent, then this part, the just probability of B. So it would be probability A times probability of B, right? So for example, here in this cell here, what's the probability of A1 and B1? That means what's the probability that somebody volunteered for 1 to 3 hours and came from what? Community college student, community college. So what's that probability? Well, in chapter 3 we learned how to find probabilities, but here the probability, we want the number of volunteers based on probability that is here. So what's the probability that somebody volunteers this many hours and comes from community colleges? Well, to find that probability, what we have to do is this. We have to take probability of A1, right? What's the probability of A1? Would be 298 divided by what? 839. So 298 divided by what? 839. So that's the probability of what? That's the B1. Now, what's the probability of B1? Or probability of B1 would be, let's see, B1 total is 255, so that's 255 divided by, again, 39. So that would be the probability that somebody comes from community colleges and volunteers for 1 to 3 hours, right? That's the probability. But if we take this many people, based on that probability, if they're independent, how many people we should have had here? Well, let's see. We're going to multiply that by what? By the number of volunteers that we surveyed. And this number is what expected to be there if we assume that these two variables are what? Independent at this level. So if A1 and B1 are independent, the number we should have gotten here is this. Now we're going to calculate this number for every cell. But this looks a little tedious. Can we find an easier formula? And the answer is yes. To find the expected value for every cell, all you have to do is what? Take the total in the column and take the total in the row, multiply them, and then this cancels that. Looks like you just have to divide by the total surveyed, right? So the formula looks like, if you want to find the expected value in this cell, just take this column total, right? And then multiply it by what? This row total, and then divide it by what? The total, the grand total, sample size. That's it. So we got a formula for find the expected values easily. So let's do that. So that's how we find these numbers, right? So to get this, we get the total in A1, 298, multiply by total in this row, 255, and divide by 839. To get the one here, we get again A1 total times B2 total, so A1 times B2 totals divided by 839. And the same for every cell. And then we find all of these numbers. Here we go. We got them all. So if we assume that these two variables are independent, we should have gotten what? These numbers in these cells. But of course, those are not the numbers that we have when we observed, right? What do we have? Well, let's compare them. So what do we have is actually these numbers, right? We got these expected, and these are what? These are observed. So again, we're going to do the same thing, very similar to what we did before. So we're going to take the observed, subtract the expected, right? At every value, and then square, and divide by what? Divide by expected, and then sum them. Now we're going to go from, let's say, I goes from 1 to what number? Well, let's see. In this case, we're going to have how many numbers? How many numbers we're going to have is number of rows times number of columns, right? So we have 3 rows and three columns and 3 rows, so 9 here, right? So we get our chi-square here. Now, when we want to compare that with, we want to find the p-value, well, where do we put this? We're going to put it here. But the question is, what's the degrees of freedom for this? And the answer is the degrees of freedom would be row minus 1, number of rows minus 1 times number of columns minus 1. That's the number that, in this case, what would that be? Well, it would be 3 minus 1 times 3 minus 1, so that would be 4 in our case, right? 3 columns and 3 rows, so that would be 3 minus 1 times 3 minus 1, 4, right? So we get the degrees of freedom of 4, and then find the p-value to the right of this, right? Well, it seems to be a little tedious to do all of these. The calculator program can do this for us. So let's do that. And I want to go back and show you the what I just described here. So the test stat for the test of independence is similar to that of a goodness of fit test, right? Here, degrees of freedom would be this number I just talked about, and so there are going to be many terms to add, but we're not going to do it by hand. So we could do it by hand, right? If we do, I'm not going to do it here, but if you do, you subtract these, square them, and divide by expected. Subtract these two, square it, and divide by this. Subtract these two, square it, and divide by this. And then add them all up. In this case, you get 12.99. Degrees of freedom is 4. So we can just put it in. So we can put it in the calculator, and the p-value would be 0.0113, right? And how do we find the p-value again? You go to calculator and you do chi-square what? CDF. You do 12.9 and then you put 10 to 99, right? And then 4. That's degrees of freedom. Okay. So at 5%, since the p-value is 0.0113 is less than 5%, we say that there is enough evidence to reject the null hypothesis. And the null hypothesis here is that the two variables are independent. The alternative hypothesis is that the variables are not independent, or they're dependent. So in this case, we say at 5% level of significance, there is sufficient evidence to conclude that the number of hours volunteered and the type of volunteer are dependent on one another. That means it doesn't matter where the volunteer comes from when we want to decide how many hours they're going to volunteer for. It does matter where they come from. All right. So how do we do this with a calculator? Well, with a calculator, it's really easy. This is probably the easiest test. So all you have to do is to create a matrix. Now, matrix is right here. So we go to matrix, and then we go to edit, and we pick the first one. The size of the matrix is 3 by 3. 3 rows, 3 columns. Number of rows goes first. So that's 3 rows and 3 columns, right? And then we put the numbers in there. So 111, that's the first. We put the observed values there, not the expected. And then 96, and then 48, and 96, and 133, and 61, 91, 150, and 53. There. All right, once we have the matrix, then we quit. Now we're going to go to stat, tests, and we're going to go to the end and pick the one that says just chi-square test by itself. Chi-square test. Pick that one. Then it's going to ask you, where did you put the observed values? Well, we did put it in matrix A. So what we do, we're going to go to matrix, and then don't go to edit, just pick number 1. There. Now, of course, by default, it has matrix A already there. But if it doesn't, then put it there. And the matrix B would be where the calculator is going to put the expected values. So calculator is going to calculate all of these for you and put them in matrix B after you run this test. So now you don't change B, just leave it alone and go to calculate. There. You see, not only it found the expected values for you, it also found the differences, squared them, divided them, and then added them, and then figured out the p-value for you already. Figured out the test stat and the p-value, see? So that's the test stat, and it's right here, and the p-value. And degrees of freedom is 4. So the p-value turns out to be 0.011, so at 5% we of course we reject, right? Now if somebody asks you, okay, what are the expected values? Well, you can go back to matrix, just clear this home screen, go to matrix and go get B. So you go number 2 and put it on home screen and press enter. Now there are too many decimal places, we only need maybe 2 decimal places, so you can go to mode and change that float. You see, if you put it on float, the calculator gives you, you use all the power of the calculator. If you only want 2 decimal places to be calculated, you move it to 2, press enter, go back and press enter one more time to run this test. You see, now they're given with 2 decimal places. Now you can go to the right and see, for example, these numbers right here. See the 49.24, 56 right there, and 56.77 right there. So you can actually find out what the expected value in each cell is if you go to matrix B. Matrix B is given you. The reason I changed the number of decimal places because there were too many of them and you couldn't see it. So change it to 2 decimal places and you see all of them. Okay, so that's how you find the matrix of expected values. All right, so that was a test of independence. Now we do another test, which is test for homogeneity. And it looks like I'm going to end this video and then make another video for the rest of chapter 11. Okay, I'm going to do this one and then test for single variance. So let me get out of this and go back here and just say bye to you, and I see you in the next video. Take care of yourself and others. Okay, bye.